All right. Okay. Okay. So here, this is remember our action has been written in the canonical form. So this is well, this is here. It is just minus h. Minus integral dt. Well, dt of h. So this is our canonical action. Suppose you do the variational principle equals to 0. What you get is just those set of equations. It's not so hard to check that these equations are just the variational principle of this canonical action. So those equations, because we know the variation of the action is Einstein equation. So therefore, those actions, those canonical actions, is just the Einstein equation. It's nothing but a different formulation of Einstein equation. Okay, so now let's come to a subtlety that, because remember that we have two constraints. Yeah, the most interesting part is how to handle these constraints. This constraint looks very simple, and they are primary constraints, but we need to make sure that the time evolution preserves those constraints. It means that suppose you start with this point as your initial condition and start your time evolution. The time evolution better stay along the constraint surface. Yeah, because all the time we have to keep these two primary constraints because the action valid at all time. Yeah? So and these formulas valid at all time, and the action at all time completely independent of n dot and ni dot. Yeah? So these primary constraint has to be valid at all time. So it means that all the time evolution has to preserve these two constraints. All right. Okay. So then it means that for the constraint, let me write down the constraint again. Pn equals to 0 and Pn vector I equals to 0. So they are both 0. So it means that the time evolution of Pn, well, which is Pn dot, equals to Pn with Poisson bracket with Hamiltonian. Well, I mean, this Hamiltonian, this can be easily compute. This is just a minus delta H delta N. Yeah, this has to be 0. Yeah. By the way, probably I have introduced this notation last time. So usually we say that this is curly equals to 0. It means that it vanishes at constraint surface. Yeah, when we write something equals to 0, it means that on the entire phase space, this guy equals to 0. But suppose we write f curly, or approximately, this is not really approximate, but I'm using this equal, it means that f vanishes only on the constraint surface. Okay. Okay, so it means both of them are vanishing on the constraint surface. And here it is also vanishing on the constraint surface. And Pn vector is Pn vector I is Hamiltonian. And this equals minus n delta ni. This has to be equals to 0 as well. Okay. And now, therefore, we get Pn dot and Pni dot equals to 0. And they are also constraints. So they are constraints derived with the consistency of the primary constraint. So these are primary constraints. So these are primary constraints. And these are called secondary constraints. Secondary constraints. Yeah. How to write down this secondary constraint more explicitly? You can see that these functional derivatives are very easy to compute because h is proportional, it's linear to n and ni. Okay, this is a linear relation. Therefore, the functional derivative of h with respect to n just gives C, and AH with respect to NI just gives CI. Okay. Therefore, those secondary constraints is just C. So delta H delta N equals to 0. It means C equals to 0, and delta H delta Ni equals to 0. It means Ci equals to 0. Okay. So these are the secondary constraints, and they are very important. The first one is called Hamiltonian constraint. And or also called scalar constraint. So this is called diffeomorphism constraint. Or it is called vector constraint. All right. So, and C and Ci has been given explicitly in this formula. So they are two most important concepts in generativity, is that you have two kind of constraints, and which are not so easy to solve. And these primary constraints, they are very, very easy to solve because they are just setting some canonical coordinate to be 0. So they are very easy to solve. But these two constraints are not so easy to solve. So you have to study case by case, and you include those equations into Einstein equation, into the equation you want to solve in the end for Einstein equation. Okay. And furthermore, you can check that. So I mean, once you get a secondary constraint, you may have question that, okay, probably you have to check the consistency of the secondary constraints. Namely, you have to compute the C dot equals to C with H equals to 0. You have to set this. I equals to Ci and H also equals to 0. So these are, probably you will call them tertiary constraints. Tertiary constraints. Well, but the truth is that they are not new constraints. So they are implied. But they are implied. They are implied by C equals to Ci equals to 0. So it means that there's no further constraint. There's no tertiary constraint. The reason is that the time evolution consistency of C and Ci, they are automatically guaranteed. So they are just implied by the existing existing constraints here. So there's no implied by that. There's no new constraint. No new constraint. Okay. So basically, our constraint, our canonical analysis finishes. So that's all the derivation for the canonical analysis. So here you can roughly get the you can get the scheme of canonical analysis. So, okay, so let me briefly review this scheme. So firstly, you have position variable. This is just the variable in your Lagrangian. After you did the canonical analysis, after you did the 3+1 decomposition, and you get those position variables, and then you derive those momentum variables, okay, by this standard relation, and then you can construct the phase space and construct Poisson bracket because you know the conjugate variables already. But in case sometimes like here in GR, you don't have n dot, the action has no n dot and ni dot. And then you get some primary constraint. Yeah. So some case when you do this, when you perform these derivation for the momentum variable, you immediately find some constraints, just like here. These are just called primary constraint. And then the next thing is that you have to write down all the equational motions and to compute the time evolution of those primary constraints. Yeah. You have to compute the time evolution of primary constraints to see if you get new constraints. Yeah, because the primary constraint has to preserve in time. Then once you have a new constraint coming from Pn dot, and you call them secondary constraints. Now here, indeed, for general relativity, you have a secondary constraint, and they are called Hamiltonian constraints and diffeomorphism constraint. And then once you get a secondary constraint, you have to further check the time evolution consistency of those secondary constraints. If you still have further constraints, if you still have non-trivial relations, they are called tertiary constraints. Yeah, so which means you have additional constraints. Yeah, and then you have to keep going to making consider the consistency, time evolution consistency of the new constraints, and keep going further and further. Right? After at some point you have to stop. But for general relativity, it is very nice because you only finish up to secondary constraint. You don't have further constraints, and the time evolution consistency of the secondary constraint is satisfied automatically. Yeah, so you will see in a few moments why they are satisfied. Yeah? So you are going to see it in a moment. Okay, so now we finished this derivation for the canonical analysis. So we can now write down the final Hamiltonian formalism for general relativity. So firstly, let me start a new page. So firstly, you have a Hamiltonian. So yeah. Let me summarize the Hamiltonian formalism of GR. So of course, for Hamiltonian formalism is formulated in terms of Hamiltonian of GR. So this is given by H integral d3x sigma nc plus ni ci and plus some boundary terms we haven't studied yet. Boundary terms, okay. And so here this C, so here you got constraints. Which is C equals to 0 and Ci equals 0. And then suddenly you find it is pretty interesting, it's pretty funny that you find this Hamiltonian, it is just a linear combination of constraints. So here this n and ni are kind of coefficients, and this C and Ci are just constraints. So here the H up to boundary term, let me say it more precisely, up to boundary terms well, this is curly equal. Up to boundary terms, H is a linear combination of constraints. Okay, this H is just a linear combination of constraints. Then it means that, well, again, up to a boundary term, H is 0. Well, where H is 0 plus boundary term. Plus boundary terms. Yeah. So you don't have any bulk terms. And secondly, this n and ni, they are just Lagrangian multipliers. They are Lagrangian multipliers. So the coefficients in front of C and C in front of constraints, they are Lagrange multipliers. Probably in classical mechanics, you have known, you have seen some examples of constraint mechanics, and then you have some parameters in front of the constraints. They are Lagrange multipliers, and you have no dynamics. So here you can see that the lapse function and shift vectors behaves as Lagrange multipliers. They have no dynamics. They are just a coefficient in front of constraints. So you can safely ignore them from the phase space. Okay. All right. So they are not dynamic. Not dynamic. All right. So so here you can see that the Hamiltonian is up to a boundary term. So even suppose you can consider some extreme case is that suppose your manifold sigma has no boundary. Okay, it's a compact space like a sphere or a torus, and then you have no boundary term, and you find that in that case for general relativity your Hamiltonian is completely zero. So there's 0 plus boundary term on the constraint surface. Yeah. So in the case that you have no boundary, the Hamiltonian of general relativity is just completely zero. Okay. And you know that Hamiltonian is usually the conserved quantity. It is the energy of the system. It means that in general relativity, there's no bulk energy. There's no energy contribution from the bulk, and all the energy contribution is from boundary. So it reflects the fact that so-called the gravitational energy is non-local. Energy is non-local. It's non-local. So here you cannot say that you point a point in the spatial slice. You consider a point at on the spatial slice. You can't say the energy density. You can't make any statement about the energy density of GR, because energy density at the point will be always like zero, because you have no bulk term in the Hamiltonian. So this is these will be your energy density if it is not zero, but unfortunately it is zero. Yeah, it is just a linear combination of the constraint, so there's no sense of energy density in general relativity. So you can only consider the energy, not the energy density. The total, you can only consider the total energy of general relativity, which means the total energy of the space-time, and this total energy, it is just given by this boundary term. So that's why we call that energy, gravitational energy, is non-local. So
as you say, if the basically compete, so you say no one tends so human that and
so if you have no boundary, then I have to say, yeah, it's zero. The energy will be zero.
It's so confusing. I mean,
it is what? It is confusing.
Yeah.
Well, well, so at least in this Hamiltonian formulation, yeah, this is just because. Okay, so this is something probably I have to talk about it now. It reflects the fact that the Hamiltonian, why general relativity has no Hamiltonian? Hamiltonian is zero. The reason is that in general relativity, the time evolution is just a coordinate transformation. Yeah, you translate in time, it is just a coordinate transformation in general relativity. But in general relativity, we know all the coordinate transformations are just gauge degree. Therefore, there's no very much physical meaning of time translation, because this is just a gauge transformation. So in that sense, there's no any physical meaning of time translation, right? That's why there's no Hamiltonian. Yeah. Yeah, because all the time translate just gauge transformation. So the Hamiltonian, therefore, this time evolution equation here, this is exactly the most interesting part of general relativity, is that this equation, although apparently it looks like a time evolution equation, but it is just from gauge equivalence, gauge invariance point of view, this is just gauge transformation. It's just a time translation. Yeah, so this is just a gauge transformation. So yeah, so then that's the reason why you have Hamiltonian equals to 0, and all the meaningful ingredient of Hamiltonian in the end is just boundary terms. Yeah, so we will come to these boundary terms at some point, probably next week. Yeah, we'll talk more about it.
Okay.
A little bit more about it. Okay, so that's a weird part of gravitational field, is that the bulk energy is just 0. You have no sense of energy density in general relativity. At most, you can talk about energy of the entire space-time as the boundary term for Hamiltonian.
Okay.
Yeah, so let me probably write down this. So because time evolution is just gauge, just the gauge transformation. Yeah. And it is not only general relativity has this perspective. And for all the system which has diffeomorphism invariant, which has for all the system, you can there are many other different systems like topological quantum field theory, topological field theory, and other all kinds of field theory has this kind of feature, that which is the diffeomorphism invariant. And suppose once you have a field theory which is diffeomorphism invariant, and then you immediately end up with a Hamiltonian which is 0, which is the linear combination of constraints and vanishes on the constraint. So this is really a general feature of the diffeomorphism invariant. All right. Okay. So so now so we have the Hamiltonian, we have the constraints, and we have a set of equation of motion, which is because we have ignore those variables like n and ni and pn and pni, they are already solved as constraints. So end up with canonical variable, which is just qij and pij. So we only need to consider the equation of motion for pij and qij. Minus qij. So these are the equation of motion, and again we have also a set of constraints. Okay, so let's call this equation 2. Okay, well, I don't want to write explicitly what is C and what is Ci, but so these are the definition of the expression for C and the expression of Ci. Okay, well, sometimes I use C upper I, and sometimes I use C lower I. So here C lower I is just the Q ij C upper j. So in the end, C lower I will be more useful when we're considering external variables and other and quantum theory. Okay, and it turns out, well, it's clear that the equation 1 and 2 completely determine dynamics of gravity. So it's completely determining the dynamics of gravity, and they are actually equivalent to vacuum Einstein equation. Vacuum Einstein equation. Einstein equation. Vacuum Einstein equation is just the GAV equals to 0. You have no matter fields. So because here in all the analysis we don't consider matter field. Okay, and more precisely, what you can check is that C equals to 0, the Hamiltonian constraint, actually equivalent to GTT, more or less equals to 0, more or less equivalent to GTT equals to 0, and CI equals to 0, it's equivalent to GTI equals to 0. Yeah. And the evolution equation 1 is well, you can here you see this Hamiltonian equation. The good thing about Hamiltonian equation motion is that they are first order differential equation, but the price to pay is that you have both position variable and momentum variable. Okay, yeah, that's when you learn classical mechanics, you probably have learned that, because the ordinary equation of motion, they are second order differential equation, but somehow you want to replace the second order differential equation by first order differential equation because they are easier to solve. Then the strategy is go to Hamiltonian formulation, and you get in the end the first order equation of motion like this. But the price to pay is that you have to enlarge your variable. You have to work with phase space, yeah, and you have both position variable and momentum variable. Okay? So that's the logic behind Hamiltonian equation. But then you can, of course, the equation of motion, they are equivalent. You can reduce from the first order differential equation of Q and P back to the second order differential equation. So now suppose you reduce. Suppose you reduce first order PDE to second order PDE, and the result is the Einstein equation. Again, if you reduce from this equation from first order differential equation to second order differential equation, you get Einstein equation, the IJ components of Einstein equation. Okay. So here the point is that, and those equation 1 and 2, they are completely equivalent to the vacuum Einstein equation. And what is good about it? So here these ADM formalism. So these are the equation of motion of ADM formalism. So these give you a initial value formulation of general relativity. So this is ADM is a initial value. Relation of GR. Okay. So what exactly it is? So namely given a 3+1 decomposition of spacetime of let's say of the manifold before the spacetime, which is just R cross sigma. And now we can formulate gravitational field as a dynamic, as a time evolution. So it means that suppose I place some initial value on certain time at sigma. So let's consider certain initial value of the field on sigma, let's say t equals to 0. So what is the initial value? It is the initial value of the Qij and Pij. So these are the only non-trivial conjugate pairs we left at t equals 0. Suppose I place some initial value on sigma equals 0, and this initial value has to satisfy the constraint, because this constraint is defined on the spatial slice. You can see that these constraints has no time derivative, so that's why we call them constraints. So they have no time derivatives; they have only spatial derivatives. Yeah, and it means that in order to be a proper initial value, they have to satisfy constraints. C, they have to be on the constraint surface. C equals to Ci equals to 0. Okay, and then by using the Hamiltonian evolution equation, you can get a solution. So because the Hamiltonian equation is uniquely determine the solution from an initial condition. Just like you have the phase space, this is your phase space P, and you have a point which is your initial condition, and then the Hamiltonian evolution just give you a trajectory on the phase space from the initial condition. Okay, and then what you get from equation of motion is that a solution Qij P below Ij is uniquely fixed. Fixed by 1 by the Hamilton's equation, by the Hamiltonian evolution equation. Okay, so that's the use of this ADM formula. Okay. And this solution is completely equivalent to G mu nu. It's equivalent up to gauge freedom, of course, up to gauge transformations, equivalent to your space-time metric G mu nu. Yeah, it's just because solving those, so 1 and 2 is completely equivalent to a vacuum Einstein equation. So solving 1 and 2 is the same as solving Einstein equation. So then it means that that we have a sort of algorithm to systematically solving Einstein equation. Is that once you have initial conditions on certain spatial slice, and then you just evolve using those Hamiltonian time evolution equation, and then you immediately get the space-time, you get the metric on the entire space-time, you get the solution. And this is exactly what one do in, for example, numerical relativity. And one just use this ADM formalism, this Hamiltonian equation, and discretize on the lattice, and perform computations to solve Einstein equation. Okay, so now let's talk about gauge transformations. New page. Let's talk about gauge transformations. Now let's recover. Let's call this recover gauge transformations of GR, because we said at beginning of Hamiltonian analysis that somehow this 3+1 decomposition breaks the gauge transformation, breaks the gauge invariance in certain sense, because this 3+1 decomposition is sort of select a preferred coordinate system. It's like at least you select a preferred time coordinate. So you sort of break gauge transformation. So somehow, but as I said before, these gauge invariance is still there. It's just transformed in a different manner. How to get them, how to recover them. And the scheme is that all those gauge transformations are now actually stored in those constraints. So those constraints are actually reflects the gauge invariance. So now let's look at these constraints, and to better do computation, we consider so-called smeared constraint. Smeared constraints. So let's define so-called Cn to be an integral d3x n of C. Okay, so here this n you can view this is they are lapse function. You can view what I write is just a part of the Hamiltonian. Yeah, so just a part of Hamiltonian. N you can view this lapse function, but here this n can be arbitrary. You can view it's just a test function. Yeah. So this is well. Let me write the Ci as well. C vector n defined to be sigma d3x n I Ci. Okay, and these all right. So this is C of n. So this is like changing. You see, before I always use C of x, for example, and x is, as I said, x is kind of continuous index. Okay, but now I just kind of making, you can view this is a changing of the variable or changing of the index. Now I use a function n to be the index. Yeah, so I'm both of them are continuous. Okay, and continuously changing. So x is continuous index and n is also continuous index because this function can be arbitrary, can be continuously changing. Okay, so it is just nothing but just changing the index. Okay, or this Cn, if you can see the discrete analog. This Cn, this is just relates to, for example, summing over I and I. Let me use A and A C A. Okay, so this A is like the analog of this X, but A is a discrete label, and this N is has a discrete label as well. Yeah? So this is a discrete analog of Cn. Can help you to understand what is going on here. Okay, so now let's compute the following quantity. So let's consider this kind of perturbation of Q and P. Okay,